Okay, so over here in Minitab, we want to run our hypothesis test to see whether or not KC1, how strong is our evidence. So we're going to do stat, basic statistics, one proportion. So we're still trying to find out information about a single proportion, in this case, the proportion who voted for Casey in all of Pennsylvania. We have summarized data. We don't have like 1,619 yeses and nos or who they voted for. What we know is that 909 out of 1619 voted for Casey. So we flip that to summarized data. This time we are going to perform the hypothesis test. So we'll check that. And the hypothesized proportion, that's our null hypothesis number. The number that we're comparing to is 0.5. Okay, so we want to know if he got more than 0.5. Look under options. So I'm going to keep using the exact one instead of the normal approximation. We need to change our alternative hypothesis. So right now it's on the default that the proportion is just something different. We want our alternative hypothesis that the real proportion is bigger than 0.5, the hypothesized null hypothesis proportion. So we're taking bigger than for our alternative hypothesis. Okay, this 95 up here in confidence interval, we're not looking for a confidence interval in this example, so that's sort of not relevant. They are going to give us a confidence interval, but that's not what we're going to be focusing on. Okay, so we hit OK, see what we get. All right, actually it didn't give us a confidence interval, did it? So we have 1619 tested, 909 voted for Casey. The proportion in the sample that voted for Casey was about 56%. Actually, this is kind of a confidence interval. I'll talk about that in a second. So they did really give us a confidence interval, but kind of a weird one. It's different than what we did before. And then this is our p-value. Okay, so remember the p-value is assuming that the null hypothesis is true, what is the probability that our sample would happen? And so that's basically like, what is the probability that the proportion in the real election that voted for Casey follows the null hypothesis, which is that half or less voted for Casey. Okay, so it says 0. I think we can actually get extra decimals. Yeah, so I right-clicked here, and it has decimal places. So I can increase the number of decimal places. Why don't I just put it up to 16, which is the maximum? Okay, so here's my p-value to 16. So it's 0.000000. There's 8 zeros and a 4. Okay, 8 zeros and a 4. I think that's like 4 in a billion. So there's like a 4 in a billion chance that this poll could happen, but Casey would actually get less than half the votes. Even if he got less than half, he might still win because there was like 1 or 2% who voted not for Barletta or Casey, but there's like a 4 in a billion chance that he got less than half. And the rest of the time, like whatever a billion minus 4 is out of a billion, that's the chance that he got more than half and won this election. So based on this poll, you could see how the news agency would feel quite safe calling the election for Casey. All right, so let me flip back to Word and we'll sort of draw some conclusions. So the p-value was equal to basically 4 times, here, let me get math up here. 4 times 10 to the power -9. Okay, so that's very small. So essentially, assuming the null hypothesis is true, the chances that this poll could happen is like 4 in a billion. That's extremely unlikely. So unlikely, we think that it's more likely that the null hypothesis is actually not true, that it's not true that Casey got less than or equal to 0.5 of the votes. So we have strong evidence that the null hypothesis is not true, that it's false. Okay, if the null hypothesis is false, then Casey won the election. And we don't know for sure, because there's still a 4 in a billion chance, and that could happen. But we are quite confident that Casey won this election once that poll is there. And of course he did win the election. He got like 55.5% or something like that when all the votes were counted. Okay, and every hypothesis test is going to have a conclusion something like this. Like we have strong evidence the null hypothesis is false when this number is very small. And when it's not very small, then we don't have strong evidence. That doesn't mean the null hypothesis is true. It just means that our experiment didn't really show that it was true. It came up with a number that said, maybe it's true, maybe it's not. Can't really prove that a null hypothesis is true using a hypothesis test. You can't even find compelling evidence that the null hypothesis is true. It's just like, it's like a counterexample test or something. Like you assume something's true, and then you run a test, and basically your test is inconclusive unless it provides evidence against it. You know, you have to look for something weird to happen. If nothing weird happens, then you don't really have any conclusive results. Okay. So a couple side notes. How small is small? So I said that this is very small, so we have strong evidence. And if it's not so small, then we don't have strong evidence. Well, what's the line? Where is the line for small enough that we have strong evidence? Okay, so you're supposed to decide what your line is before you even collect the data. You know, you're saying, I'm going to run an experiment, and I've decided that my line is 1%. You know, if my p-value comes out less than 1%, I'm going to say that that is so unusual that I think it shows evidence that the null hypothesis is false. Okay, so that line you pick, there's a name for it. It's called the significance level. Significance level. And it should be chosen before you even start collecting evidence or collect data. Okay, speaking of which, your alternative hypothesis and null hypothesis, they should also be chosen before you collect data. So should your null hypothesis and alternative hypothesis. So you're supposed to have all that stuff in mind before you even collect the data. You don't want the data to bias you and make you try to like change your assumptions to fit what came out. You know, because it's the nature of randomness that if you sort of look for patterns after, then you're going to find them. So you have to sort of like have the patterns in mind before, do the experiment, which is supposedly random. And if the patterns match what you expected, then that might actually count for something. Okay, so what are typical significance levels? So usually the significance level is 5% or 1%. So 5% is the most common. You know, 95% confidence interval is the most common confidence interval. 5% as the significance level for the p-value is the most common. Now, 5% actually isn't all that small. You know, if everybody in the class like ran an experiment, I have 60 students in 375. 5% means that like, I don't know, 3 of them on average would land in that 5% group. So If something only has a 5% chance of happening, that definitely still happens. So it's not really the best practice to have 5% be the standard, the industry standard for significance level, but somehow it's become the standard. And they use that level in things that are really important, like drug trials. So that's sort of a little bit of a flaw in statistics. In this case, we got our p-value to be 4 out of a billion. That's way lower than 5%. This actually is strong evidence. But if something was close to the line here, like it was like 4%, that's still small enough that it's below our significance level. But, I guess we decided that 5% was small enough if that's what we chose, but it's not really that small. So anytime there's a scientific paper that relies on stats, if they use 5%, you have to take it with a grain of salt. Like, it might have been luck, especially if their p-value is anywhere near 5%. If it's like in single digits and not like a decimal, then yeah, it might have been luck that made it happen. Okay, one last thing that I wanted to mention before I end the video and end the class for today is in Minitab, we had this confidence interval, except it didn't look like a confidence interval. It wasn't a range between two numbers. So this time, they just gave us a lower bound. So we said the vote for Casey, there's a 95% chance that the lower bound on that is 0.54. So they actually gave an interval there. It's like 0.54 up to infinity. And the reason that it only has a line on one side and then it goes all the way up forever on the other is because we didn't do the standard alternative hypothesis of not equal. We kind of did it on one side. We only did the bigger than side. And so the confidence interval they gave us was only the bigger than confidence interval. If you look at the exercises in the textbook, they often specify two-sided confidence interval. And so what they mean there is the one that has bounds on both sides, not a one-sided one like we got this time. So if you're using Minitab, to make sure you get the two-sided one, your alternative hypothesis has to have the not equals set in there. Okay, so that's it for today. I'll put the homework in the notes as usual, and remember, we now have quizzes every day. So I'm going to put a quiz on D2L that's similar to part of the homework.